Suppose I have a little yellow ball again, and suppose that I want to find the potential energy. Now the potential energy, I'll call it PE, is given by the formula mgh. So in this case, for example, let's say the ball is 0.2 kilogram, so that's the mass, and the h is the height from the ground. Let's say it's 1 meter. So that's my h. And g, we know what g is. G is 9.81 meters per second squared. So we know how to find potential energy, and we know the meaning of that the formula is mgh. And we also know what happens when we drop the ball. Just before the ball hits the ground, the potential energy of the ball would become 0 because h has dropped to 0, but the exact amount of this mgh would be converted into its kinetic energy, which is half mv squared. So the exact amount of half mv squared just before it hits the ground is the potential energy. So that's our understanding of potential energy from because of the gravity that comes from the gravity. Okay, so that's going to be our starting point. Now, what I'm going to do in this and maybe the next 1 or 2 sessions is to think about how to extend this idea to the case where this object is very, very far from Earth, very high above the Earth. Meaning, let's see what I mean. Meaning that if I imagine lifting this object up until it's hundreds or even millions of kilometers away from Earth, then we need to look at Earth from outer space. That's Earth, and this little ball is now a great distance away. Now, can we still talk about the potential energy using mgh? Probably not. Okay, the g here in this formula is assumed to be fixed at 9.81, and we know that if we are very far from Earth, this g, which is also the gravitational field strength, which is also the force per unit kilogram, decreases. It becomes very small when you're that far from Earth. So surely that has to change, and I cannot just change the value of g to its new value here either, because what if this ball falls all the way to Earth? Then the g is going to increase from a very small value to a very big value. So what g do I use? So things would get a little bit more complicated. Now, to develop the understanding of what we need to do, let me come back to this. Right, the first thing we need to do actually is to understand the meaning of potential energy better, starting from something that I've mentioned in the past. Now, if you may have seen from an earlier video, when I talked about having a table, alright, having a table, okay, and I talked about how you can also define h as the height from the table, right? So the h can also be the h from the table instead of this. So I can change this to this h. So it'll be a different h. And the way we dealt with this is that instead of thinking about the potential energy as a fixed amount of energy that the ball has. Okay, unlike the case for kinetic energy, we know that if the velocity is v, then it's a fixed amount given by half mv squared. We can think about the potential energy instead of a fixed amount of energy. We think of it as a way to help us calculate the work done by the gravity and the kinetic energy we would get if it falls, if the ball falls. Now what this means is that if I change my h to here, let's say the table is maybe say half a meter high. So let's say this height here is 0.5. If I refer the ball's height to the table, okay, then I have a different potential energy. Okay, I have a different potential energy. So surely when the ball falls to the ground, the kinetic energy, I cannot just obtain the kinetic energy just before it hits the ground, just by calculating mgh using this value of h. Surely I must use this value of h because this is the h that it falls through. So the method that I described previously is that we think of this level, the table, as a reference level. So let me write this down. I think of this as a reference level. Okay, so that when I think about mgh, the meaning of mgh, I think about it as work done against the gravity. If I need to bring the ball from here, let's say I will have the ball here at the beginning and I bring it all the way up to there. So this is actually the work done to bring let's see, a body, in this case the ball, a body, okay, from a reference point to its position, okay, to its position. So mgh, think of it as the work done to bring the ball from, if I define this to be my reference point, the table, the work that I need to do to lift the ball up to there against gravity. So let me put in some notes here. The work done is the work done by me, not by gravity, okay, by me or by you. Yeah, you get the idea. So by not the gravity, just by a person or by something else, to bring a ball, okay, against the gravity, all right, to bring a ball in this example, okay, against the gravity. Okay, so these are just some comments here for this example. But these two brackets, ideas in the bracket may vary with the situation, but we'll see. Okay, so it's the work done to bring an object from there to there. Okay, and we know that this work done because h is distance and mg is the force that I need to exert against the gravity. So force times distance is work done. Okay, so we're here now. And then with this understanding, if I take this as a reference level, then in order to we can still use this potential energy formula and this value that I got to find the kinetic energy when the ball hits the ground, except that we can't just do mgh. We need to do a little bit more work. Okay, the way to do it is this. First, we need to find the potential energy when the ball is here. Okay, let me call this position A. Okay. Now then I need to find the potential energy when just before the ball hits the ground. Let me call this position B. So I need to find two values of the mgh, and then if I subtract those, I will get the kinetic energy. Let's see how it works. So let's say this is 0.5 of a meter. Then let's say this height. So this height here would be also 0.5 of a meter. Now, one thing we need to do is to treat the h as a displacement, meaning that I need to take a positive direction for h. So let me choose up to be positive. So therefore, when the ball is up there, the displacement from the reference level is plus 0.5. Just before the ball hits the ground, it's the h, all right, from reference level to here must have a minus sign, because this ground level is below, it's on the negative direction, below the reference level. So what I can do is I can find the potential energy at A and B. So let me do that. I want to find the potential energies, and I want to find it at A, and I want to find it at B. Now, to find the potential energy at A, I must use this formula, mg times h. Okay, so it's mg, where m is the 0.2 kilogram, g is 9.81. So we know mg. Now the h in this case is plus 0.5 meters. So plus 0.5. Now that's at oh, I want to find it at B first. Right. At B, the height is minus 0.5, so minus 0.5 meter. Now at A likewise is mgh, but the h now is plus 0.5 meter, so mg and plus 0.5 meter. Okay, so I have the potential energies at the two levels. Now the way to find the kinetic energy here is to say that the kinetic energy here must be equal to the decrease in the potential energy. The decrease in the potential energy. So I can find the change in potential energy by taking the potential energy at B and subtracting the potential energy at A. Now if I do that, I'll get mg. Now if I take mg, the common factors, out of a bracket, I can find, well, I'll have minus 0.5 and minus 0.5 in the bracket. So that gives me mg times 0.5 is 1 times 1. In this case, times minus 1. So this is the same magnitude as if I had measured h from the ground. Okay, if I measured h from the ground, it is 1 meter. If you remember, I had this 1 meter here just now. So meaning that by defining this reference level and by treating h as a displacement with, in this case, a plus and minus direction as a displacement, then I can find the kinetic energy by finding the change in the potential energy. By taking the final potential energy and subtracting the initial potential energy, I will still get the same answer, right, regardless of where I choose my reference level. Previously, I had chosen my reference level to be the ground level from where I measured the h to be 1 meter, and I calculated, and I know that I can find the kinetic energy using mgh. But this time, I chose the reference level in a different place at the top of this table, but using this additional procedure, these additional steps, I can still find the answer. Okay, then there's the question, why go through this trouble? Why go through all this trouble? Can't we just take the ground level as the reference level and always measure the height from the ground? Why must we measure the height from a table? After all, some tables are higher, some tables are lower. Isn't that a lot of trouble? It is more trouble indeed, but if you think about it, it does not really make things a lot easier, even if you take the ground level as the reference level. Because suppose that this is the ground level in a house. What happens when you go out of the house to the field outside? You may need to go down some steps before you go outside into maybe to a park outside your house, and then the ground level will be different. Okay, and then when you go to another place which has a slightly higher ground, perhaps, or a slope, the ground level would be different again. So it doesn't really make things a lot easier. So in general, right, it actually is better if we can always define a fixed reference level, or at least fixed for the places that we want to go to, we normally want to look at, and then always measure the height from that same level. And then using this rule of subtracting the final and the starting potential energy to find the change in potential energy, and to say that change in potential energy, the decrease in potential energy, would be exactly converted into the kinetic energy. So just to summarize what I've described, what I'm saying so far, is that don't just take the potential energy as the formula mgh itself. Okay, we need to also remember that the formula for the potential energy needs this information about the reference point, right? Because the height has to be measured from some reference point. So potential energy has a few things that we need to know before we can use it correctly, before it has the proper meaning. So one thing is that the height or the position must be measured at some reference point. So we have to know where this reference point is, and we can actually decide ourselves where we want it to be, just some convenient place that is fixed and that we can always refer to. It's fine. Tabletop, ground, in a park, in the middle of a mountain, no problem. Just remember where you fixed it. Okay, that's one thing. Now the other thing about potential energy, okay, well, I just described the meaning of potential energy. Now the other thing about potential energy, which is equally important, is what you use it for. Right? It's no use just getting a number and say that potential energy is 20 joules. Alright, it's okay, but it's not very useful. Now the other thing about potential energy is that we would normally use it to calculate kinetic energies when the ball drops. In this kind of example, right, we would want to know when the ball drops from one level to another level, what's its increase in potential energy. So this is the use of potential energy, and that's equally important. And with this understanding, all right, using the reference point definition, we can and using this method of finding the change in potential energy, we can calculate the kinetic energy that we get when a ball drops just by finding the change in potential energy. Okay, and the change in potential energy will always be the same no matter where you choose reference level. All right, if the ball falls from one level like A to another level, the change in potential energy that you will find will give you the same answer whether you choose the ground level to be the reference level, in which case you just do mgh to find the PE, or if you choose somewhere else like the tabletop as a reference level, in which case you have to calculate two different mgh with the two different h's, with plus 0.5 and minus 0.5, and then you have to subtract them. But when you subtract them, you end up with the same answer. So having a different reference level will still give you the same change in potential energy when the ball moves from one position to another position. So we think of the potential energy as a means of calculating kinetic energy.